So in this video here, I'm going to continue on with chapter 19, and I'm going to look at another equilibrium constant, except this one is called Kp instead of Kc. Kc, the C in Kc stands for concentration, and the P in Kp stands for partial pressure. And that's because when you've got a reaction that only involves gases, you often use the partial pressure instead of the concentration. Now, you don't always have to do that. If you watch the previous videos, there's lots of reactions that we looked at, the Haber process, for example, where everything was present in gaseous form, and we still went and worked out the concentration at equilibrium. But in other cases, when you've got a reaction that involves gases, instead of giving you concentrations or asking you to work out concentrations, you'll instead be asked to work out a partial pressure. And in terms of which one you're supposed to do, you look at the question. They'll either ask you for Kc, and they'll give you moles and volume, and you'll be able to calculate concentration, or they'll ask you for Kp, and they'll give you things like mole fractions and total pressure. So it'll be quite obvious which one you are supposed to be calculating. In terms of the initial expression, very similar to what we saw with Kc. In Kc, though, you'll remember we used square brackets because the C stood for concentration, and square bracket means concentration. Here, the P stands for partial pressure, so I'm using this little value, this little P here, to show partial pressure. But other than that, it's the same as before. I take what I've got on the products, and that goes on the top line. If there's any numbers used to balance, you raise it to the power, and then on the bottom line, I've got my reactants. There's no big numbers there, so I don't need to raise any powers. And again, I'm not using square brackets. I'm not dealing with concentration. I'm dealing with partial pressures instead. So the way you'll write these Kp expressions will be very similar. As with the Kc, there is a difference between homogeneous and heterogeneous equilibrium. So if I just give you an example of a heterogeneous expression, H2O as a gas reacting with carbon as a solid, and that goes to H2 as a gas and carbon monoxide as a gas. If I was writing a Kp expression for this, I would take the partial pressure of the H2, I'd be timesing it by the partial pressure of the CO. Again, I'm avoiding those square brackets. And then on this side, I would be leaving out the carbon because it's a solid, and I'd just be including the H2O. So I'm going to include everything that's a gas. I'm going to leave out a solid. If I had something in liquid form, I would leave that out also. I'll just do one other example of this. I've got CaCO3, which is a solid, breaking down to give me calcium oxide, which is a solid, and CO2, which is a gas. So again, if I was dealing with partial pressures here and I asked to write for an expression of Kp, on the product side, the only thing present as a gas is CO2, so I'd include my CO2. I'd leave out my CaO, and then on the reactant side, again, I've got another solid, so I'm also going to leave that out, and that's my entire Kp expression. Once you've written your expression for Kp, you'll often be asked to solve for Kp. So when we had Kc, you needed to work out concentrations at equilibrium. When you've got Kp, again, the P stands for partial pressure, you'll have to work out partial pressure. And partial pressure is quite straightforward to work out. Partial pressure is just mole fraction, and I'll show you what mole fraction is in a second. It's mole fraction times the total pressure. So the easiest thing to do would just be to look at an example. So I'll start off by just looking at an example for how you calculate mole fraction, and then once we are comfortable with mole fraction, we'll look at a question, and we'll calculate Kp. So if you are doing mole fraction, I'm just trying to find a question here where they ask you to do it. Yeah, here we go. All right, I've got a question here. It says I've got a gas mixture, and it tells you the total pressure, 320 kilopascals, and it says you've got 3 moles of nitrogen and 1 mole of O2, and I want the mole fraction and the partial pressures of each gas. So I've got 2 gases in my mixture. I've got N2 and I've got O2. The first thing I'm going to do is I'm going to work out the mole fraction of N2. And if I'm working out the mole fraction, I need to look at the total number of moles of the gas, and then how many of those moles are nitrogen. So it tells me that I've got 3 moles of nitrogen and 1 mole of O2. So my total number of moles is going to be the 3 for nitrogen plus the 1 for the oxygen, will be 4. And when I'm getting my mole fraction, I take the number of moles of nitrogen over the number of moles of the total. And I get 3 over 4. The mole fraction of nitrogen is 0.75. If I were to calculate the mole fraction for oxygen, okay, I said 3 moles were nitrogen, 1 mole was oxygen, so I put the 1 on the top this time, and then I've got 3 plus 1 again at the bottom, and I end up with an answer of 0.25. To check that you've got your mole fractions right, add them up. They should equal 1. If they don't, you've made a mistake. So as I said above, once you know what your mole fraction is, you times it by the total pressure to calculate the partial pressure. In this particular example, it tells me that the total pressure is 320 kilopascals. So if I times the mole fraction by the total pressure, I'll work out the partial pressure for nitrogen. And if I times the mole fraction of oxygen by the same total pressure, I'll work out the partial pressure for oxygen. And then the units for partial pressure will be exactly the same as the units I've got here for total pressure. So we'll just look at another example, one here underneath, sorry. It says I've got 10 centimeters cubed of O2, 25 of N2, and 15 of H2. So in this time they've given you volumes. We need to know moles, okay? But if I wanted to go from a volume to moles, the little kind of triangle I would be using, this one here, I'd have moles. I would have, wait, pen. There we go. It'd be this one here where I've got volume at the top, moles here, and molar volume, which is the number 24. So if I took each of these volumes and divided by 24, I would find moles. But because you're dividing by the same number for each one, the ratio between the 3 of them is going to be exactly the same. So it's basically arbitrary. You don't need to divide them all by 24. If you're dividing them all by the same number, overall it's pointless. So I can just take those volumes and I can use those volumes directly to calculate the mole fraction. So they're telling me I've got 3 different gases this time. I've got O2, I have got N2, and I've also got H2. And the oxygen, they're telling me that 10 centimeters cubed is oxygen, so I put the amount that's oxygen at the top, and then at the bottom I want the total. So I've got 10 of oxygen, I've got 25 of nitrogen, and I've got 15 of hydrogen. So that adds up to 50. So I've got 10 divided by 50. I should be able to do that in my head, but I can't. Multiple 2. And I get 0.2. And then for nitrogen, they tell me it's 25 as nitrogen over the total. Yes, I can do in my head. It's 0.5. And then for H2, I'm going to have 15 over 10 over 25 and over 15, and this should work out as being 0.3, and I know it should work out as being 0.3 because when I add up the 3 mole fractions it has to give me 1. I'm just going to confirm that adds up to, and yes it does, 0.3. So if I add up my 3 mole fractions I should have an answer of 1. If you don't, you've made a mistake. And again, once I know my mole fractions, if I want to work out the partial pressure of oxygen, I times by the total pressure, which I'm given in the question. So I'm timesing that by 500 kilopascals. I'm timesing this by 500. I'm timesing this by 500. So work out the mole fraction first for each gas, times it by the total pressure, and you'll get the partial pressure for each gas. And it's the partial pressure, the values you calculate for partial pressure, that you will then go and fill in into your KP expression. So we'll look at a full example here where we actually calculate KP. And the reaction I've got, again, it's the Haber process, which just comes up all the time. And as I said in the previous video, if you've watched it, we looked at Kc. I also use this equation a lot. But because all of the species are gas, you can also calculate Kp for this reaction as well as for Kc. So I'm going to start off by writing my expression for Kp. All right, so I'm going to take what's on the product side. Remember, I'm not using square brackets. Squared over the P of partial pressure of N2 times the partial pressure of H2, and that's going to be cubed. But in order to solve for Kp, I'm going to need to work out the partial pressure for each gas. And to do that, I'll just remind you, partial pressure is mole fraction times total pressure. So if I look at the question, I should be able to work out these things. So it tells me, if I just zoom in on the question part as opposed to the solution, it tells me that at equilibrium, and it gives me the temperature, I've got 18 moles of N2, 54 of H2, 48 of NH3. I can use those values to work out the mole fraction for each gas. And once I know the mole fraction, I'm going to be timesing it by the total pressure, which I'm also given in the question, to calculate the partial pressure for each gas. So I'm going to write down the gases I've got. I've got N2, I've got H2, I've got NH3, and I need to work out partial pressure for each of them. But to do that, I need my mole fraction. So I'm told in the question I've got 18 moles of N2. So it's going to be 18 divided by the total number of moles. So I've got 18 of N2, I've got 54 of H2, and I've got 48 of NH3. So that's going to be my mole fraction for nitrogen. And once I've worked out my mole fraction, I times it by the total pressure. So I'm timesing it by 200. I'm going to work out my partial pressure for nitrogen, which is apparently 30 atmospheres. So again, my total pressure is an atmosphere, which means my partial pressure will be 2. For hydrogen, I'm going to do the same thing. But the value for hydrogen is 54, so I'm going to be putting 54 on the top line, and then on the bottom it's still going to be 18, 54, 48, timesing it by that total pressure, and I get 90 for hydrogen. And then for NH3, the value for NH3 is 48, so 48 goes on the top, the bottom line stays the same, so that should be a plus, not a multiply. Bottom line stays exactly the same. I multiply by 200 and I get 80 atmosphere. So these are now my partial pressures, and once I have my partial pressures, I just plug them back into that expression. So it's going to be Kp equals, for NH3 is 80, so it's going to be 80 squared on the top line. For N2, I said it was 30, and then for H2, I said it was 90, and that's going to be 90 cubed. So I fill in all of those values and I work it out as being 2.9 by 10 to the minus 4. And again, you're asked for your units. And you're filling in these values here, and they're all in atmosphere. So if I wanted to work out the units, I've got atmospheres squared at the top, I've got atmospheres there at the bottom, and then I've got atmospheres cubed. So what I can do is I can cancel, those two will go, 2 of the 3 will go, but I'll be left with 1, and then I'll end up with 1 over atmosphere times atmosphere is atmosphere squared. When I bring that atmosphere squared above a line, I'm going to get atmosphere to the minus 2. So it's going to be 2.9 by 10 to the 4 atmosphere to the minus 2. Just over here, I'm just going to highlight this example in the book. It asks you to calculate HP for a heterogeneous equilibrium, and it gives you the reactions. We've already written the Kp expression for this reaction, and we saw that we had to leave out the calcium carbonate and the calcium oxide because they were both solid. That meant my entire Kp expression was just Kp equals the partial pressure of CO2. In the question, you're told the partial pressure of CO2, so you weren't even asked to figure it out. You're just told straight up what the value was, and then I'm just plugging that value straight into the expression, and I'm getting Kp equals this. So the value of Kp is the same as the value of the partial pressure of CO2, because that's the only thing that remains in the expression once you get rid of your solids. So again, that would be kind of reflected in the number of marks going for the question. There's no calculation needed there, so probably just be a 1-mark question, and that should alert you to the fact that you don't have to do quite as much work as in the example that we just did. All right, I'm going to do one of the exam questions on this. So I found something that's not the Haber process. So I've got methane and water reacting to give me hydrogen and carbon monoxide. You'll see everything is present as a gas, and they've asked you to calculate Kp. They do give you some other information because it's part of another question, but in this particular bit, they're asking you to calculate Kp and to show all your working, and they're actually giving you 7 marks for this. So this is from the old spec. We don't typically see 7-mark questions anymore. But if I know I'm calculating Kp, then I know I need the partial pressures for each of these. And if I want partial pressures, I need mole fractions and I need total pressure. If you look at what they've given you here, it tells me the number of moles of CH4 and the number of moles of H2O that you initially add to the sealed container. And then it tells you how many moles the equilibrium mixture contains. you're trying to find the Kp for the equilibrium. So when you're getting the mole fractions, you need to know the moles you've got at equilibrium. These two values here are not the moles you've got at equilibrium, they're the moles you've got at the start. They're your initial moles. So just like in the previous topic, we're going to have to do a rice box. We're going to have to calculate the number of moles at equilibrium for each of the 4 species. Once we know the number of moles at equilibrium, we can calculate mole fraction, and then we can go from mole fractions to partial pressures by multiplying by the total pressure. Once we've got all of our partial pressures calculated, we can then plug the numbers back in to the Kp expression. So I'm going to start by doing my rice box. And again, it's telling me to show all of my working, so that's what I'm going to do. So I'm going to do my rice box, the R-I-C-E. And the first thing I'm going to do is my ratio. So the CH4 is 1, the H2O is 1, the H2 is 3, and the CO is 1. So I'm just getting those, so I'll just write above which one each one is. I'm just getting those from my balanced chemical equation. Initial moles of CH4, I'm told, is 1. The initial moles of H2O, I'm told, is 1.4. And I know the initial moles of H2 and CO is going to be 0, because they're the products, and at the start of the reaction, they're not going to be present. The other piece of information I'm given is the equilibrium mixture contains 0.2 moles of CH4. So they've told me at equilibrium, I've got 0.2 moles. So I've started with 1. I've only got 0.2 moles left. That means that my change is going to be minus 0.8. So again, it's always going to be minus for your reactant because it's being used up. If I'm starting with 1, and I'm ending with 0.2, the change must be 0.8. And once I have even one value written in there for change, I can fill in all of the rest of the values just using this ratio. The CH4H2O, the ratio between them is 1:1. So if I'm using up 0.8 moles of methane, I'm also using up 0.8 moles of H2O. And again, I know that sign is negative because the reactants are moved up. So then I can go 1.4 minus 0.8 is 0.6 moles of H2O. Between methane and hydrogen, I've got a 1:3 ratio. And again, for my products, it's going to be a positive change. I'm starting with nothing and I'm making some products over the course of the reaction. So it's going to be 0.8 multiplied by 3, 2.4. So I started with nothing and it's increased by 2.4 to give me an equilibrium moles of 2.4. And then I look at my ratio at the end, and again it's 1:1. So if it's 0.8, then it's going to be 0.8 here. And again, it's going to have a positive sign because I'm making the carbon monoxide. So my 0 plus 0.8 is going to be 0.8. So again, your ratio and your change, they have to align. The ratio in your top line has to match the ratio of the numbers in the bottom. You can see here I've got 1, 1, 1, and I've got 0.8, 0.8, 0.8. And where I have a 3, I've got 3 times 0.8, 2.4. Just pay attention to your signs. Reactants are going to be minus, products are going to be plus, and then I can use initial and the change to work out equilibrium moles. So now I've got the equilibrium moles, okay? But I want partial pressure. And if I want partial pressure, I need mole fraction times total pressure. So normally at Kc, when you got to this point and you had moles, you divided by volume to find concentration. Now we're trying to find partial pressures, so we're going to have to find mole fraction and then times it by total pressure. And once we've done all of that work, then we can fill the partial pressures back into a Kp expression. So for each one, I'm going to have to work out the partial pressure. So the partial pressure of CH4 is going to be the mole fraction. So the number of moles of CH4 I have at equilibrium is 0.2. So mole fractions, you're always calculating it at equilibrium. That's why this rice box was needed. I couldn't just plug in the 1 from the question into this expression. I need the moles at equilibrium. So it's going to be the moles of CH4 divided by the total number of moles. And if I add up the number of moles for all 4 at equilibrium, I get a value of 4. So it's going to be 0.2 over 4, and then I multiply by the total pressure, and the total pressure, it's given to me in the question, and it's 30 atmospheres. So it's going to be 0.2 divided by 4 times it by 30. And that works out as being 1.5 atmospheres. So my total pressure is given to me in atmospheres, which means my partial pressures are all in atmospheres as well. Then I work out partial pressure for H2O. This time the total number of moles of H2O is 0.6, and then the total of all the moles is again going to be 4. I multiply by the same total pressure, and I get a value of 4.5 atmospheres. For H2, the partial pressure, again, is going to be 2.4 divided by 4 times by the total pressure times by 30, and that gives me 18 atmospheres. And then my partial pressure for the last one, for carbon monoxide, I take the number of moles at equilibrium, 0.8, divided by the total number of moles, which is 4, times it by the total pressure, and I end up with an answer of 6. And in a question like this, if you want to make sure that you haven't made a mistake, add up your partial pressures. They should equal your total pressure. So my total pressure is 30. If I add up these 4 values, you will see that you get 30, and that helps you know that you are right. So when you're adding up your mole fractions, we actually haven't worked out our mole fractions, but if I did 0.2 divided by 4 and 0.6 divided by 4, and I just did that part, and I added up all the mole fractions, it should equal 1. And then with your partial pressures, when you've got them worked out, they should equal your total pressure, which in this case is 30. So you've got a long question like this, it is worthwhile checking your work as you go, making sure you're still on track. So now I've worked out the partial pressure for each of these, but I'm asked to work out Kp. So I need to write an expression for Kp using my balanced equation, which I'm just going to squeeze in up here. So Kp is going to equal the partial pressure of H2 cubed times the partial pressure of CO, and that's going to be over the reactants. I've got partial pressure of CH4 times partial pressure of H2O. And then I would take these partial pressures that I've worked out down here in atmosphere, and I would plug those values into this expression, and I should end up with an answer of 5,184 when I plug in those numbers and solve. In terms of your units, all of our partial pressures are in atmospheres, so it would be atmospheres I'd go in, plug in. On the top line, I've got atmospheres cubed times atmospheres. On the bottom line, I've got another atmosphere times atmosphere. So those two will cancel straight away, and that one will cancel out one of these. So it's going to go from atmospheres cubed to atmospheres squared. And because that's already on the top line, I don't need to go from bottom to top. There's going to be no changing in sign. Your unit is just going to be atmospheres squared. So again, with these questions, make sure you are showing all of your working. They are for a lot of marks. It is easy to make a little mistake as you go. So in order to get your error carry forward, you need to make sure you have got all of your working clearly shown. You also have a few little tricks that you can go and make sure that your mole fraction is right. You can make sure your partial pressures are right. It will help you know that you've definitely got the right answer.